Forget the Swiss rolls, search out the mini Big Bangs.
I wanted to find out how the universe really is, to discover the secret plans and hidden schemes behind creation. Why is the whole show the way it is? I wanted to see how much about everything you could cram into one head. This one. I'd been on one hell of a journey, back to the beginning of space and time, the Big Bang. I'd been told all the matter in the universe was created in the time it takes to boil an egg. Quite astonishing, really. But how could all these tiny particles of something emerge from nothing at all? I'd fought my way through to the middle of Stephen Hawking's book. Now I had to deal with the contents of the universe, matter, and the forces which hold the whole show together. The story of the atom starts with the Greeks. The ancients were split between those who thought you could go on dividing up matter forever and ever, and those who thought
that matter was inherently grainy, and that everything was made up of large numbers of atoms. The word atom means indivisible in Greek.
It was a good idea, this. If you could look right into the fabric, to the smallest atom-sized crystal, you'd find each substance had a unique shape. Ooh, a dodecahedra went by. Now, the tiniest speck the Greeks could imagine was 1/10,000th the size of the smallest mote of dust in a sunbeam. Now, you have to fast forward a couple of thousand years for the next theory of matter. This emanated from the Hubble bubble of alchemy. The old alkies got respectable when they invented the chemical elements. They said each element had different-sized balls. So essentially to them, the world was a load of balls. Actually, that's pretty much my own view. The old school physics was coming back to me. Atoms are very empty things. Swirling electrons that circle that hideously small dot in the middle, the nucleus. But even this crude view of the atomic universe was about to be shattered as Campbell entered the unreal world of the quantum. So far, the reality show is going all right. But now, I had to brace them for the journey to the edge of nothingness, where we would encounter nature's inner secrets. Subatomic particles. Just to give you an idea of a subatomic particle. You heard of an atom, Daisy? An atom? Right, imagine an atom now, just in your mind, to be the size of the Albert Hall. We're talking about something like a speck, less than a grain of sand now. We're talking about to the atom, right? Now, to get inside an atom, I found I had to come to Switzerland. Here, hidden beneath the snow, is the world's largest experiment, where they study the world's smallest things. This is CERN. To provide enough power to breach the atom, they divert half the electricity supply of Geneva. 17 nations must pool their resources just to turn on the switch. This underground magic ring casts its spell in every direction, as matter meets antimatter in head-on collision. Here they knew the secret of how everything was created out of nothing, just like it was at the dawn of time. I was to leave Sir Isaac's world of classical physics and enter the realm of King Albert, where matter disappears and reappears in the CERN ring of truth. My guide to the labyrinth was an enthusiastic Finnish chap called Hanu. Yeah, in Tenerife, these guys have got, like, enormous gramophone horn. yeah, with which they claim they're hearing the Big Bang. Yeah, it sounds a bit. At the bottom of this shaft, they produce strange, unstable particles, some not seen since the universe began. It all sounded a bit dangerous, but they assured me it was totally safe.
All around the ring, they have these big experiments. We have several of them, not only one.
The ring, Hanno explained, is a racetrack to accelerate the particles. And what they do here is a bit like the reverse of the atom bomb. Instead of converting matter into energy, they perform an amazing stunt. They turn energy into matter.
What CERN is, chaps and chappes, is a 27-kilometre tube. They built that underground there, a 27-kilometre tube. The tube is entirely empty. It has nothing in it, but then on some ancillary bit, they're generating subatomic particles.
The particles don't whiz along here, do they? It's not in this tunnel, not that we're in.
No, we are now in the main 27-kilometre tunnel.
Yeah.
And inside these blocks is a tube, which is, actually you can see it there.
That tube there?
That tube there. That is where the particles are moving.
How fast are they going?
Oh, these particles which are moving in there are moving almost with the speed of light, and that means 300,000 kilometers in 1 second. So this is 27 kilometers, the ring, and that means they move around 11,000 times every second around the ring. And
11,000 times a second?
A second, around this circular ring.
Right. And then when they collide, that's energy. Energy is produced, which then falls into matter again.
Again, matter.
But a different sort of matter.
Right. We get all kinds of particles. We get
then you say it doesn't matter?
Yeah, right. It doesn't matter what kind of matter, because all matter is just energy. Yeah. Energy and matter are the same thing.
I was about to confront the only equation in Stephen Hawking's book.
E = mc squared.
I approached it with caution.
Okay, Ken. Energy equals mass times the speed of light squared. That c squared is a dangerously large number. Each unit of matter the equivalent of 1 trillion units of energy. So, where is all this energy and matter? That's half a gram of matter in front of you. Let's burn it. Watch those atoms dance as the bonds between them break. Next, try half a gram of high explosive. Damn, those atoms can fly apart, but these, Ken, are just chemical reactions. You ain't seen nothing yet. If you convert the matter itself into energy, half a gram would make a blast so enormous, it'll destroy an entire city.
Hello? Hello?
Hello, qu'est-ce qui se passe?
Don't worry, I'm English. We're just doing an exercise.
Oh, right. There's nothing gone off or anything?
No, just a fire surface exercise, that's all.
Oh, I see. Well, because it's potentially quite dangerous here, is it?
Well...
Oh.
Okay, so we're going to get the lot of you out and up onto the ground, okay?
Yeah, we're moving you out now.
All right, okay.
That's great.
I was with this guy, Hanno. You didn't see him, did you?
Yeah, we're going to go and look for him. We'll take our breathing apparatus and go and find him.
While we're being evacuated, a few CERN facts to ponder. Fact 1, CERN would never go off. Fact 2, most of CERN is 100 metres underground. Well, that's 500 steps when the lift's out. Fact 3, the ring is so large that the gravitational pull of the moon affects the experiments.
Excusez-moi.
Oh, there you are. Hey.
Oh, good.
I thought I lost you.
I did lose you. We were now ready to consult the oracle and visit an experiment they called Delphi, where they produce types of matter that haven't been seen since the universe went bang.
But you're actually making big bangs, is it? Or little big bangs?
Yeah, little big bangs, right.
Yeah.
So, okay, so now we are here, and that is the hall.
This is like Westminster Abbey or something.
Yes, just the physical size is like a big cathedral. And,
What is this altarpiece?
Yeah, the first building, 3 stories, is nothing but a computer. One computer, and
this entire thing.
Yeah, this is a specially made computer, and just behind that is the detector itself that will see the particles.
When these things collide, how is it seen? I mean, can you see how? I mean, they're rather small, these boys. And so what they've done is they've built a computer rather larger than Westminster Abbey down here. And it's all pipes and stuff and each other. And I said, what is it? I said, is this old? He said, an old one. You know, they're not using modern technology. I said, no, it's up to the mark. Listen, these chaps, when they appear, you know, these particles, you know, I have to give them new names. One of these, they have to give them names. They've never been seen before. When they appear, they appear for a hideous, tiny fraction of a second, you know? And so you need the whole Westminster Abbey computer in order to know it happened, you see?
Just take me down from an atom. There's an atom which is composed of
a nucleus.
Of a nucleus,
and
electrons going around it.
Yes, and we pick out these electrons.
You can do that. You can get one electron.
Yes, and then we put them in the accelerator. So
how do you get an electron?
Oh, just use a magnet. Electron will follow a magnet. So we take a magnet, we pick out electrons, we rattle the atoms a little bit so the electrons are falling off, and then we use the magnet to guide them to the accelerator.
So you've got your nucleus of an atom, and you've got these electrons, which are always to be found going around the nucleus of an atom.
Yes.
Except here, you're able to get one off.
Yes.
And then you send it on a 27-kilometre journey.
Yeah, like a racetrack.
Right.
Yes.
And to collide, and it collides with a what?
With another beam, which goes in the opposite direction. So we have 2 beams.
Beams.
Yeah, beams of these electrons. There are millions of electrons.
Millions of electrons.
Yes. So the 2 beams are moving in this accelerator. They're passing by.
Can I just get this right? So 2 particles collide.
Yes.
And particles being points.
Yes.
Right, of no dimension.
No dimension.
Things of no dimension, but are able to be sensed.
Yes.
By yourselves, yeah. And these things collide, right? And from them springs matter.
Right.
What they do at Delphi is to decipher the debris of this smash. It's a kind of accident investigation computer.
The detector has been opened so that we can really see well what is happening in here. So this is
on the day we were there, the engineers maintaining this monster had peeled back the core. The tiny particles are detected by the massive metal grapefruit segments.
This fits in there.
This fits in there when we are operating. And up there is the accelerator which is going through Delphi. So the collisions are taking place just in the very heart of Delphi.
And then it's sensed by all this, is it?
Yes, all these plates, you see, these are the plates sideways, and the particles are flying through, and when they are flying through, this piece is a detector.
What, the new particles actually come through this?
Yes, they are flying through that. These are the eyes we are using, in a way.
The eyes.
Yeah. And so this plate will know that an electron was hitting in there, or positron, or whatever, maybe a completely new particle we have never seen. Yeah. And then it will send the message through the cable to the big computer. But let's go up to see where the collision really happens. Watch your step, this is dangerous.
Right. The heat generated is a heat that ain't been seen since the time, gents, of the Big Bang. You know, the Big Bang, no, just imagine, let's go back to the Big Bang for a moment. Imagine how incredibly hot it must have been, you know, at the time, to go off, you know, and there's you and me and everything like that, and all the rest of the whole show.
Into the eye. Hello.
Yeah. Hello.
Come on in.
So, now you can see the accelerator is coming in, and the end cap is
this high-class drain pipe has attracted top boffins from all over the world.
If you got it a bit hotter, I mean, would you create a whole new universe would begin, would it? An actual Big Bang in the middle of this one?
No, I don't know that, but basically we are studying.
You don't know that?
experimentally. Yes.
But it might.
It might, yes.
We need a bigger accelerator than what we have at the moment.
Yes, but you're getting one, aren't you?
Well, not as big.
Right.
To start a new universe.
Yeah. How big would that one be then?
Pretty big, I think.
So this was it, the point in the tube where the magnets bend the particle beams into a collision course. Hannu hit me with a very fruity analogy to help me understand what was going on. Imagine strawberries and anti-strawberries smashing into one another, he said. What do you get? Not squashed strawberries, but a whole blooming fruit salad. You end up with more matter than you started with. Bigger particles emerge. Such is the strange but true story of the creation of matter. Of course, you can't actually see these collisions. The Westminster Abbey-sized mega-brain has to reconstruct the event.
You can see here, this is actually how the detector observes that. All these spots are sparks which are produced by one track, the collision.
Yeah.
Now this is, of course...
It looks like a whole spray of them, but is that just one?
Yes, this is one track. Actually, the human brain and the human eye are so powerful tools that we don't only want to read numbers from computer, but we want to make it visual. So the physicist has actually drawn, using these spots, the real tracks of the particle. Coming out
these curving ones here?
Yes, these are particles, new particles produced.
In there, from a collision?
Yeah, coming out from the collision.
The events inside this particle circus ring had left Campbell wondering what these things are. Some particles seem to be point-like, and some seem to be rather overweight. Oh, and I'd learned a rather disturbing fact. The fundamental particles have mass but no size. How could this be? I had an audience with the Prince of Quarkness.
Ah, hello. John Ellis?
Yeah.
Ken Campbell.
Oh, yeah, I recognise you. Pleased to meet you. Please, take a pew.
Thank you. Now, you're the head of theory.
That's what they tell me, yeah.
Thank you. Thank you. Does that mean you don't do anything?
It means I have to do two things. First of all, I have to do my own theory. The second thing is I have to help the other guys do their theory.
I see. Do particles have size?
Well, the things that we call elementary particles, the things like the quarks, the electrons, even the Z particle, as far as we can tell, don't have a size.
Yeah.
I mean, they look just like, idealised points, a little bit like in Euclidean geometry.
A proton, a neutron, has size.
Ah, yeah, but that's a bit different because...
But how can a component part of something that has size not have size?
Well, you can think of a proton or a neutron as maybe being a little bit like a bag, which is about 1/10 of a millionth of a centimetre across. And then you can imagine these quarks rattling around inside that bag. So the size of the proton is actually given by the distance over which these things rattle, okay? Although the quarks themselves are actually, as far as we can tell, idealised point-like particles.
They're idealised points. But so do they exist then?
Oh yeah, they certainly exist. I mean, we see them coming into our detectors as showers of other particles like protons and photons and so on and so forth.
I really can't cope with this no size. If you say something doesn't have size, does that mean you can't measure it? We haven't decided on any word for such smallness.
Yeah, in fact, see, our accelerators are a lot like microscopes. And we could very well be that if we built a bigger accelerator, higher energies, we go to smaller distances, that actually we'll be able to resolve, say, a quark or an electron and find that it's actually a composite object like a proton or neutron. The problem is to understand why some particles, like, for example, quarks or electrons or Z particles, are heavy, and other ones, such as the photon or the particle called the gluon, which holds the quarks together inside those proton and neutron bags. The problem is to understand why some particles are massive and other particles are massless.
So when you say massive, you just mean it has mass?
That's right. Some of these guys are really massive. Like, for example, the Z particle, which we make here at LEP, it weighs like something about 100 times as much as a proton. So it weighs as much as a fairly hefty nucleus.
Time to get some of this data in order. First, it seems that all matter and all forces, everything, comes in particles. And the smallest particles within a nucleus are called quarks. There's up quarks and down quarks stuck together in bags by force particles called gluons. Photons stick electrons around the bags to make atoms. All the rest, the muons, the taus, beauty quarks, strange quarks, leptons, neutrinos, are just collector's items. I can see why they need robot librarians to keep track of all this data. Come to think of it, I could do with one of these ladies at home to keep the place tidy. It was only after all this that it struck me. I didn't actually know what a particle really is. Incidentally, in case you were wondering where the name quark came from, it was named by a well-read physicist, Murray Gell-Mann, who spotted this line. 3 quarks for Muster Mark. It's from James Joyce's Finnegan's Wake, another in the Campbell collection of great unread books. You see, quarks work in tight little teams of 3 inside the nucleus. They can't bear to be alone. James Joyce would have relished this next conversation.
The quark is like a prisoner who tries to escape, but the vacuum has developed a beautiful mechanism to catch escaping prisoners. It boils policemen out of the vacuum, and these...
Some people collect stamps, certainly collect quarks.
So there's up quarks and down quarks, and anti-up quarks and anti-down quarks.
Hello, how are you?
Hi, yes. I have been...
I'm well collected.
I have been showing Ken around the ring yesterday, and we went to Delphi, and he's asking so many difficult questions. I cannot answer them all, so I will ask your help.
I'll try.
Okay.
Okay. Did you have your coffee?
Not yet, no.
Yeah. So let's get some. Okay.
There's something rather heady about the CERN canteen. The magic ring attracts brains from all over the planet to ponder the essence of quarkness.
At the present moment, we all believe that it's firmly established by experiment that a large class of so-called elementary particles consists of these quarks, which makes it very beautiful, because if you have 100 different particles and you can reduce their existence to a handful of others, you have made a great deal of simplification, you know? Assume, for instance, that there would be nothing in the world but red and white bricks. Assume there would be no blue bricks, no gray bricks, no black bricks. You could say, I've discovered the basic particle of buildings. There are only 2 things out of which you make buildings, red and white bricks, and that's the end. So the fundamental unit of buildings is the red brick and the white brick, and that's the game we are playing.
Right.
I might assume also, well, show me one of those bricks. And it turns out that the moment you remove the brick from the building, it disintegrates. So I can't show you a brick, but the evidence is there that inside the building, in the walls, there are these units. So our evidence about the quarks is totally compelling, but we have never seen a free quark.
What I was beginning to realize was that you can never actually get at these quarks. You can only deduce they're there from the debris of subatomic prangs.
What we do is like trying to find out who lives in a house without ever being able to enter that house. And among the many things that we do, we observe the rubbish that these people dispose of. And from that rubbish, we also try to reconstruct who they might be, what their profession might be, what their habits might be. So we study the rubbish, the decay products of these particles, so as to conclude to their nature.
Bizarre!
Is that clear?
Yeah.
Okay.
Yeah. Inspiring.
I wouldn't say that the rubbish is inspiring, but at least everybody's familiar with it.
Yeah. Oh, well, this is a plaster cast of a broken foot, probably a skier.
This search through the debris of particle collisions to decipher the nitty-gritty of matter was graspable as far as it went. It was when I found out that these particles can act like waves as well that I really started running into trouble. And it kept coming back to tantalize me.
In fact, the word particle is not a wonderful word because you always think of a little ball and not of a little wave.
Yeah.
And some people have used the word wavicle.
Wavicle?
Yes, so as to tell everybody that, careful, it does not always act like a little ball. It sometimes acts like a wave and sometimes acts like a ball.
So a particle waves along?
If you wish. But again, you're doing what comes naturally to you. You're borrowing from your everyday language.
Yeah.
Okay, I mean...
Yeah. Is that why that guy tipped with Finnegan's Wake?
That's right. That's right. I mean, one can try to describe these things, and one has a tendency to do so in everyday language, but with great care, because these things are not the kind of objects that we are used to. So therefore, it's only with great caution that we should use everyday words.
Now here was an interesting riddle. Particles sometimes seem to act like waves, and sometimes like little balls. Trying to imagine the wavical nature of particles was rather perplexing. Yet this idea would fundamentally change my view of matter and its place in the universe.
Whether this object appears to you as a particle or as a wave depends on the experiment you do. So it's your choice. In other words, in certain experiments, it exhibits its wave-like nature. In certain experiments, it exhibits its little ball-like nature. But
what do you mean they try to please the professor?
They've tried not to please, they tried to how shall I put it, they try to strain his imagination. I don't think they have any morality in trying to please us.
Ken, you made it. Welcome to the quantum room. Now, what if you were a wavicle, Ken? A chemical? You would be in a sort of schizoid state, part wave, part particle. Faced with two doorways, you wouldn't go through one or the other. The wave side of you would go through both simultaneously. Now you've reached the heart of the quantum dilemma. As a wavicle, you could be in two places at once.
Can you help me with this being in two places at once?
Yeah, I know it seems a bit weird, but, let me tell you about this twin slit experiment, which I think really, shows the point, okay? We've got a board or something with just two little holes in it, okay? You shine the light onto the screen through these two slits, okay?
Yeah.
What you find is a very strange pattern, which is what we call an interference pattern with all sorts of bumps and dips in it.
Okay? Where do you find this? On the screen?
On the screen, yeah. You can imagine this as like a photographic plate.
So light has gone through there and then gone waggling up and down the screen.
The interpretation of this result is that the light has in some sense gone through here and also gone through there.
If chemicals were balls, they'd go through one slit or the other and end up piled up in two neat stacks on the far wall. But that is not what happens. Instead, there are chemicals creamed out all along the wall. Fire one photon through the slits, just one, and it goes through both. And each time it emerges, it ends up in different positions on the screen. Now, this is weird because it means that one photon, a single speck of light, appears to interfere with itself. Here was one of the central planks of quantum mechanics. I was beginning to understand its rather unnerving implications. Okay, brief recap. I want to make sure you get this.
Now, what happens with the twin slit experiment is, imagine you've got a couple of slits, right? And all we're going to fire, we'll just imagine one slit first, all right? And we'll fire light at the one slit, right? The light will go through that one slit, okay? And we'll narrow it down to just one what do we call it, package of light, a photon. Like one photon, doing, yeah, it goes through that slit. One photon. Okay, now we're going to have two slits, yeah? And we fire our one photon, doing, and it's gone through both. If there are 3 slits, it's going to have gone through the 3. And if there are 37, it's going to have gone through the 37.
The trouble with these damn wavicles is that if you do one experiment, they behave like a particle. You do another, they behave like a wave.
I mean, because you're pretty clear on this. I mean, gee, last Thursday, you know, we made our 2 slits, and the thing behaved like a particle. This doesn't happen.
It does not happen. No. I promise you that whenever you do the 2-slit experiment, it's always going to look like a wave, right?
Yeah.
You can do the same experiment with neutrons. Okay,
yeah.
So neutrons are very different from photons. They're massive particles. They travel very slowly. You can do the exact self-same experiment, get an interference pattern just like this for photons.
So, we're certain about that?
Yeah.
I understood what was being said, but that's not the same as believing it. Apparently the quantum world is a slave of probability, the dice rules, and it's this fundamental uncertainty in the world that allows such peculiar things to happen. The path of a particle is not certain, but probable, each one fluttering in a perpetual state of dither.
Controversial ways, for example, of measuring the charge of a quark and convincing yourself that it's minus 1/3 or plus 2/3, anyway, a fractional charge.
I've noticed an uncertainty thing. If I say quark, you say quark. If you say quark, I say quark.
Well, I guess that's one of the quirks of us particle physicists. We never quite decided whether it was a quark or a quark.
Mm.
It weighs like something about 100
Ellis was losing me.
photon. So it weighs as much as a fairly hefty nucleus.
Or was I losing Ellis? Can you sort out your... Maybe they're asleep. Guess I'll have to do it myself then. Well, this really calls for an experienced quantum mechanic. Oh, mind. I wonder what the problem is then. Maybe it's this. Oop. Probably not. Oh, this is more like it. I'd better explain what's going on here. You shouldn't get the idea that this quantum business is some airy-fairy notion only boffins need worry about. Without quantum mechanics, your telly wouldn't work at all. See, these little silicon chips thrive on uncertainty. Silicon doesn't conduct electricity. What happens is that electrons instantaneously jump along the wires. Because of uncertainty, electrons have no idea where in the universe they really are. So in a way, they are everywhere. Hey, maybe there's just one really nippy one.
I would think it'd probably jump rather than take all possible paths instantly. I mean, to take all possible paths would mean what? That just this little thing was suddenly everywhere every place in the universe just for a moment, and then elected to actually just to go half an inch from where it was. He went, whoop, like that. I'm here, everywhere, there. The jump part of a jump is not the landing or the taking off, it's the in the air bit is what a jump is. So when you say jump, it's quite easy, fine, it jumped. And you're saying, yeah, but you're saying, but there's no middle bit of the jump. There's a takeoff, there's a landing, but there's no middle bit, you know? It's like being on one bank and another bank, and you get across the river without a bridge or wading or a ferry boat.
I instantaneously jumped to chapter 4, the uncertainty principle.
The uncertainty principle had profound implications for the way in which we view the world.
Yeah, what exactly is the uncertainty principle?
Well, according to quantum mechanics, the only sorts of predictions that we can make are probabilities. We can say that there is some probability that this will happen, but there's also some probability that it will not happen. We can't be sure about anything anymore.
So, is the uncertainty ours, or is it its? Or is it both, I suppose?
It's. Okay, it's just intrinsic to the laws of physics.
So it doesn't know what it'll do next?
Absolutely.
So no wonder we don't.
Right.
But would we if it did?
I'm sorry I lost that. Maybe we could have a...
Right.
in there somewhere.
Okay. You're saying it doesn't know. It is uncertain. A particle is uncertain what it might do next. It doesn't know.
Yeah. According to quantum mechanics, we cannot measure at the same time the position of a particle, for example, and its momentum.
Yeah, but that's due to our patheticness.
Now, it's intrinsic to the laws of physics. Okay, now, if we're particularly pathetic...
No, right, when you say we can't, are you saying we can't, or it cannot be measured by anything?
It cannot be measured by anything. And if we devise our experiment in a particularly pathetic manner, we may cock up the measurement of the position or the momentum in such a way that the uncertainty is even bigger than what it is according to quantum mechanics.
Yes.
But quantum mechanics says that there is a basic, intrinsic, absolute limitation on how well we can measure position and momentum. We cannot measure them both perfectly at the same time. And it's the same thing with...
But is a thing is actually somewhere?
If it is somewhere, then you don't know how fast it's going, you don't know what momentum it has, and of course that means that shortly afterwards it's going to be somewhere else and you don't know where.
Yeah. But that's fine, I'm okay about us not knowing which it'll be. What I'm saying is, though, but at a given moment, it is one thing or another, or halfway between, whatever it is. We're not talking about things being in 3 places at once, one thing being in 3 places at once, or anything, are we?
Oh, yes, we are. Oh, yes, we are. Before you make your measurement, there is no meaning to the statement where the thing is. There is some possibility that it's here, some possibility that it's there, and those two things are superposed. Now, when you make an observation, you somehow squeeze the thing down to one of those possibilities.
It seems that uncertainty is not just my problem. It's a problem that has dogged scientists since the wavical nature of material objects was first discovered back in the 30s. There's a celebrated paradox called Schrödinger's cat, a thought experiment where the very existence of the cat depends on a quantum event. If the radioactive crystal decays, it will release a deadly poison and kill the cat. If it doesn't decay, the cat will remain alive. Nuclear decay is an uncertain process. Maybe a radioactive atom will decay, and maybe it won't. But quantum theory says this is not an either-or. The radioactive atom both does decay and doesn't. Only looking will squeeze it down to one or the other. So what does this do to everyday objects like cats? Is a cat uncertain? Here is a mystery of the universe that has not yet been unlocked by science. If you look up a cat with a radioactive crystal and link it via a Geiger counter to the poison and don't peek, you're in the dark. While you wait, you don't know whether the poison release has been triggered or whether the cat is still alive. You've got problems. If you don't look, they say, then the radioactive atom decays and doesn't decay. The Geiger counter clicks and doesn't click. The cyanide gas escapes and doesn't escape, and the cat dies and doesn't die. Only when you look will the cat be either dead or alive. Now, obviously, this is ridiculous. But this is the conclusion of modern physics. The greatest brains have been pondering this paradox for over 50 years. Which is to go, quantum physics or common sense?
There's the cat, look.
Missed it.
Look at that, Jack. There is a particle coming in, it is hitting another particle, and you see all these particles coming out. I call this the witch's brew, you know that.
In my search for the origin of matter, I was still not clear how particles can just burst out of energy.
Actually, I remember when I saw a picture first time like this. 20 years ago, I was a young student. I was so fascinated exactly by this kind of question. What is it coming from? And then I was told it was born there and it died there. And I said, hey, how do you know that? That's when I got the first idea, I want to become a particle physicist. I want to understand better what happens.
But 20 years on, they still don't understand. Not really. I mean, they give all these little fellas funny names. They seem to appear and disappear as if from nowhere into nowhere. When there was absolutely nothing before the Big Bang, where did the energy that created these particles come from? While this big question lurks in the background, they carry on hunting for undiscovered particles, like the elusive Higgs boson.
Higgs boson.
What I didn't, I've neglected to mention, and I wish I had because it would have made the discourse more elegant, is that none of the scientists so far would ever talk about before the Big Bang.
The concept of time starts only from the Big Bang. We cannot, for that reason, we cannot even talk about it, probably, about what was the time before the Big Bang.
Then they said, no, you can't, because time begins. At that point, when that little point, that red hot beyond belief, point in the grand celestial bugger all globe, and right, they went up, you know, I mean, climbing back, you know, like the scientists can get to a second before it, then they're going to fraction of a second and they can't get past, you know? They said, man, time began then. That is when time began, and we are in time. You can't ask the question, what happened before the Big Bang? And I always did, and they always said, well, it can't. See? I always tested them out, and it can't. But then, I met the top man of CERN, and he would talk about before the Big Bang. And he was in charge of the great experiment. He was the top man of the flipping thing. In Italian he was, you know, with the grey hair and everything like that. I mean, he spoke English much finer than me, really. You know, with a charm and everything, twinkle, sexy. Like that, a melody, you see.
He began by opening my eyes to a new problem. What determines the particular type of particle that is created from raw energy?
How can this energy density know that in the world there can exist electrons, quarks, beauty quark, you heard this name?
Yes.
Strange quarks,
yeah.
And there are anti-quarks and so on. Where is this information? How can you imagine that this happens in your mind? How can you figure out where is this information needed to know what particles have to be created? Where is it?
I don't know. Well, maybe in these tiny things there are secret schemes that we know not of.
Ah, that would be an idea.
We were now getting to the crux of the problem. That fault in the nothing, the hidden plans that must have existed before Big Bang.
And now here it comes, the new world. The word is fields. You ever heard about fields?
Oh, fields?
Fields.
He said before the Big Bang were fields. He said, when I say field to you, what does it mean to you? I said, well, it means grass, cow on it. Yeah, he said, well, don't mean fields like that. He said there were fields of potentiality before the bang.
Vacuum, the nothing, has a potentiality. This is a potentiality of being excited. You see, a field is something which is tenuous, it has no material nature, but it is there if you want, in very simple terms. But if you pour energy into it, by pouring energy on the field, which we call an electronic field, you can create an excitation.
So this
a wave.
Right, so if you remove everything, then the nothing isn't exactly a nothing.
Exactly, and that's what we do at CERN.
What?
We just study the nothing, the vacuum we call it, the physical
Really?
vacuum.
I didn't realise this. Well, so you're more interested in the nothing?
Absolutely. We don't care about matter. Matter is an accident, is a detector of what happens. But really, what we care is the nothing.
He said, I think the experiment at CERN is about the nothing in the tube. He said, what we're exploring here is the nature of no thing at all.
It seemed that nothing had a new definition. There was a kind of invisible, undetectable blueprint for matter locked in the nothing. These were the fields that tell the energy how to turn into matter.
You know how many fields we think there are around in the world nowadays? Give a number.
Just in our world?
Yes, to explain what you see around you, what we have learned at CERN. How many you feel there will be?
I mean, countless billions.
No, 37.
37?
Different fields. That is the minimum number of fields that we need to explain all what we know about particle physics.
Really?
They're different nature. There is the electronic field.
You could do the whole show with 37?
Yes.
I was sure there weren't 38. Well, he said, that's a good question. He said, there might have been 38, but there certainly weren't 36. He said, it could not have been done. He said, this whole show of the universe could not have been done with 36. He said, you need 37.
The fields that guided the birth of the universe are ever present. The secret schemes behind the mini Big Bangs at CERN.
It seems to me that you're saying something new to me. I mean, I had heard that I mean, I had to swallow it because chaps who knew seemed to be telling me that energy, it wasn't the particles that chipped off other particles off themselves.
Yes.
No, but that energy turned into particles,
yes.
at least for a moment,
yes.
and then they didn't, and
yes.
then they were back again.
Yes.
But you're saying that didn't happen.
No.
You're saying that this collision turned on some feeling in the field.
Which were there beforehand.
Which was there beforehand.
Absolutely.
They said, oh, it's my moment.
Yes.
And they flashed, or they particled, or
and then they start to oscillate, these fields, and these oscillations go away, and these are the particles, what you call the particles.
So this was the theory of nothing for all those scientists lost in the wilderness of uncertainty. Uncertainty in the wavicle. Uncertainty at the dawn of the universe. I'd moved from a load of balls bouncing around the Campbell brain to a wave on the foreshore of creation. Perhaps there was only one fundamental truth left.
So where did the originating energy come from?
We don't know.
Let's see.
This is one of the questions. We don't know where the fields came from the starting point. This is really one of our big questions. We have some ideas. You know,
I've not heard this before. So you're saying the fields precede all?
In my picture, or what I can describe to you,
this is what you're
like
saying.
that.
Anyway, certainly, yeah.
That we must have a certain moment, a lot of energy put in these fields, and so
put in the fields, I see.
By somebody, by some process.
Right.
The fields are there. There is a lot of energy. You know.
So there was never nothing. There was fields.
Yes, but maybe before there was something which was a precursor of this field, something which obliged this field to exist. You see, but what it is, we don't know.
God.
And this energy came from something, maybe. And people think about fluctuation of the vacuum.
A fluctuation in the vacuum. Perhaps this was it, the beginning and the end. Intrinsic uncertainty, the key. Although we can't be certain, but the quest is not over. I still need to square the miniature problems of the improbable quantum world with the big problem we call the universe. I was almost ready for the big man of everything.
If we do discover a complete theory of everything, it should in time be understandable in broad principle by everyone, not just a few scientists.
So it's all fields. It's just fields of potential. Whole thing. Forever. Expanding. Held together by the glue. If it wasn't for number 37, if it wasn't for the 37th field,